Hi, this is John Whitaker for the graduate level probability class. And this is our 16th video lecture. And today we want to continue our discussions about types of convergence. We had looked at convergence pointwise earlier, and today we're going to look at convergence known as almost sure convergence or convergence for probability 1. And the other type we're going to look at today is convergence in probability. And then what we're going to do is we're going to state and prove the strong law of large numbers, which has to do with almost surely convergence or convergence with probability 1. So let's go ahead and get started by giving the definition of what it means to converge almost surely with respect to a probability. So we'll let f sub n be a sequence of functions defined on a common domain, and we'll say A is a subset of R. It doesn't have to be that, okay? Then the sequence f sub n converges almost surely that's AF type convergence, that's the way we abbreviate it, to a function f, or I should say with respect to a probability P to a function f on A if, here's what we're looking for, the probability of the set of x's that are in A such that the absolute value of f sub n of x minus the f of x is greater than or equal to epsilon, that I should say the limit, as n goes to infinity. Okay? But that this probability equals to 0. And that's true for all epsilon greater than 0. So that's what it means to converge almost surely with respect to a probability. And before I move away, what we're saying is, and I'll write this down, that the probability of the set where the f sub n of x's don't converge to f of x, that's what this is, probability of that set is 0. I'll write that down. That is the probability of the set where f sub n of x, or f sub n, does not converge to f is 0. Now let's look at an example. So let's re-examine an example we had earlier. So let's let f sub n of x be defined to be x sub n on 0 to 1. Then this sequence of functions converge to big F equals 0 on 0 to 1. Almost surely with respect to the probability defined by I'll put this in quotes, the smallest length of an interval which contains the set. So we're defining probability on subsets of 0, 1, and the way that we define probability on this subset is that probability is the length of the smallest interval that will contain that set in some sense, okay? So smallest length of the interval. So if there was some separation here, you know, if you went, talk about the subset here from 0 to half and then from maybe 3/4 to 0.8, we take the sum of the smallest intervals that contain those. So there's some kind of notion here about the length of the subset, and that's the probability that we mean here. And this S of n that we looked at before, that sequence does converge to 0 almost surely with respect to this type of probability. But remember, that isn't what it converged to point-wise. It converged to 0, not on 0 to 1, but 0 on 0 up to 1, but not including 1. And then the function converged to point-wise also was 1 when x is equal to 1. So there's a difference there. They don't converge to the same thing. So let's look at a fact that relates pointwise convergence to almost sure convergence. So that fact is the following. If the sequence f sub n converges pointwise to f on a, then f sub n converges almost surely to f with respect to any probability but the previous example shows that the converse isn't always true. Just because you converge in almost surely with respect to a probability does not mean that you converge pointwise to that same function. Well, let's look at another type of convergence. It says a sequence of functions f sub n defined on a common domain A, which is a subset of R, converges in probability to a function f on A if, here's the criteria we need, if the limit is n goes to infinity of the probability of the set of x's and element of A, such that f sub n of x minus f of x is bigger than or equal to epsilon, that equals to 0. And that's for all epsilon greater than 0. So here, as opposed to almost sure convergence, where we have a probability of a limit that's defining the function, here it's a limit of probabilities. So the limit of the probability, so the limit of the measure of the set, where there's some distance between f sub n of x and x, that goes to 0 as n gets bigger and bigger and bigger. Okay. All right. So let's write down a fact that relates convergence almost surely to convergence of probability. So if f sub n is a sequence of functions that converge almost surely to f on A, then, let's say, with respect to probability P, then the sequence f sub n's converge in probability to f. Okay, with that being our probability that's involved in this definition. So pointwise convergence implies convergence almost everywhere, and almost everywhere convergence with respect to a probability implies convergence in probability. Now, to see the converse of this statement is not true, that is to see that convergence in probability does not imply convergence almost surely, we'll look at the following examples. Let me write out what I'm trying to do. To see that convergence in probability does not imply convergence almost surely. This is an example. Consider the following sequence of functions. So I'm going to show these sequence of functions graphically. Okay. The first two functions, we're kind of grouping them together. The functions are going to be defined on 0 to 1. All, that's our domain. So here A is equal to 0 to 1. And the f sub 1, I'm going to find it to be 0 on that region along the x-axis. And f sub 2 for all these x values between 0 and 1 is going to be defined to be 1. So that's my first two functions. What we're going to do is group some functions together that kind of change where they are 0 and where they are 1. And the next grouping of these sequence of functions, the next grouping of functions in this sequence, they're going to be two more of them grouped together. So f sub 3, what it's going to look like, again, it's defined on 0 to 1, but from 0 to a half, it's going to be 1. Now, I closed interval here. And then open interval here. F sub 4, again, we're going to break the interval from 0 to 1 to 0 to a half and a half to 1. Except the part where f sub 4 is non-zero will move. So here, it'll be 0 up to 1, up to 1/2. But after 1/2 and beyond, it'll be 1. So here's what I want you to notice. Over here, in both of these two functions, the region where f of 3 or f of 4 is not equal to 0 is a half, the region, the measure of that, when we think about the length of the interval. Well, now I'm going to have 4 functions grouped together. So here's f sub 5, and what we're going to do is break up the interval from 0 to 1 into 4s. And f sub 5, it's going to be defined to be 1 from 0 to a 4, and from then on it's 0. F sub 6 is going to be defined similarly. So from 1/4 to 1/2, f sub 6 is going to be 1. And then on the other regions within 0 to 1, it's going to be 0. F sub 7 of x, it's going to be 1 between 1/2 and 3/4, and otherwise going to be 0. And now f sub 8 is going to be 1 only in the region from 3/4 to 1, and the rest of the time it's going to be 0. So within this grouping of the functions within our sequence, the spots for all of these particular functions where the functions are non-zero have measure, length. They're in intervals where they're not 0. Have length of 1/4. So I'm thinking that the probability is going to be that length. Okay, we continue to form the functions in the sequence in the same manner. Okay, I'm going to write this up in just a second, but let me go ahead and go through this. So we keep on in the same manner. And what you see as n gets further and further along, as we go through creating more and more functions within the sequence, the region for which the function won't be 0 keeps getting smaller. So here it's a 4. The next grouping, it'll be an 8. The next grouping after that will be 16. And that's the probability where it's not converging to 0. So the limit of the probability is getting smaller and smaller and smaller where it's not converging. And so that gives us convergence in probability. However, what happens is that this, this sequence, I should say, of functions converge in probability to the 0 function. However, the sequence of functions do not converge almost surely with respect to this probability to 0. Because if you take some point in here, what happens is that every once in a while, it'll bounce away from 0. So there'll be some region where it's up at 1, okay, within the sequence later on within a function later on in the sequence. So what we get to say is the following. So this sequence, f sub n, converges in probability, and in this case our probability is this length, to f equals 0. But does not converge almost surely with respect, and I'll call it again, to the length of the interval. It is not technical, it's just the idea. Probability. Okay, well, the next thing I want to do is state and prove, and this is really the last thing we'll do for this lecture, the strong law of large numbers. Okay, so here's what it says. It says, let x of 1, x of 2, forever, be a sequence of independent and identically distributed random variables each having finite mean, so the expected value of x of I, we're going to call it mu, so it's finite. Okay? Then, with probability 1, okay, that means almost sure convergence with respect to this probability. The x of 1 plus x of 2 plus all the way up to x of n over n, okay, that converges to mu. So that sequence of that type of random variable converges to mu. Okay? Okay, almost sure. That's what convergence is. So we're going to do the proof of this. So let's have our setup so that x of 1, x of 2, wherever, be a sequence of random variables. That are independent and identically distributed. Suppose that the expected value of xi is equals to mu, which is finite. And we will prove this statement, even though it's true without this condition,
with one more assumption, so that it makes the proof manageable. We also assume the expected value of x sub I raised to the 4 is finite.
So we need to show that this sequence of functions, so as n gets bigger, this sequence of functions, so this is S sub n, if you will, or F sub n. And we've got to show the convergence to that big F equal to mu. All right, we're going to do this in cases. But before I get to cases, we will define that function, that fraction, by, or help by, let S of n be the sum as I runs from 1 to n of x of I. So that's the top part of the sequence of functions that we're trying to show converges almost surely to mu. Okay, we're going to look at two cases. So case 1 is if mu equals to 0. All right. Now what we're going to do is we're going to examine the expected value of S of n raised to the 4th power. So if we look at that, well, that's equal to, I need some room, is the expected value of, well, what's S of n? So it's x of 1 plus x of 2 plus x of 3 plus all the way up to x of n times x of 1 plus x of 2 plus x of 3 all the way up to x of n times x of 1 plus x of 2 plus x of 3 all the way up to the addition up to x of n. Again, we have x of 1 plus x of 2 plus x of 3 plus all the way up to the addition of x of n. So we're taking the expected value of that product. And so, if we were to multiply all that out, which I'm not going to do, and then the expected value of, we'll get a big sum. The expected value of a big sum is the sum of the expected value of each one of its parts. So what I'll say is that the expected value of S of n raised to the 4th will consist of the addition of terms with certain forms. So the addition of terms of the form, well, let's see. You could have the expected value of x of I raised to the 4th. You have x of 1 times x of 1 times x of 1 times x of 1. That's one example. You could also have the expected value of x of I raised to the 3rd times x of j. You could have the expected value of x of I squared times x of j squared, where the I and j are different. You could also have the expected value of one of the random variables twice, and then two other random variables involved in the multiplication, x of j and x of k. And you could have the expected value of 4 random variables that are all different in index. So x of I times x of j times x of k times x of l. Now, because of the case that we're in, and because of independence, it's going to we're going to be able to show that this type of expected value, this type of expected value, and this type of expected value are all 0. Let me show this. Well, note
the expected value of these types of terms, x sub I cubed times x sub j, because of independence, this is equal to the expected value of x sub I cubed times the expected value of x sub j. But in this case, we're saying the expected value of x sub j is 0. And so that's 0. So those terms really don't contribute. This term here, the expected value of x of I squared, x of j squared, x of j times x of k. Well, that's equal to, because of independence, x of I squared times the expected value of x of j times the expected value of x of k. That's this first guy times this guy right here is 0 times 0, and that's equal to 0. Finally, the expected value of x of I times x of j times x of k times x of l, that's equal to, due to independence, expected value of x of I times expected value of x of j times the expected value of x of k times the expected value of x of l, each one of which, in this case, is 0. And that's equal to 0. So the expected value of s of n raised to the 4 just consists of terms that look like the expected, it's the sum of terms that look like the expected value of x of I raised to the 4 and the expected value of x of I squared, x of j squared, where I and j are different. Let me write that up. So the expected value of s of n to 4. Well, remember it's the expected value of x of 1 plus x of 2 all the way up to x of n times itself 4 times. We've got those only two terms, the types of expected value terms that are going to be involved. So the first one is going to be the sum, well, of the terms of what? The expected value of x of I raised to 4. And so how many of them are you going to have? Well, you're going to have I running from 1 to n. Okay? So you're going to have x of 1 times itself. X of 1, x of 1, x of 1, x of 1 for each one of those 4 listings of s of n being multiplied together. Same thing for x of 2. Okay, that's okay. Plus some sum, I don't know how many is here. Yeah, x of I squared times x of j squared. Okay, I'm not saying how many. These are all the same, okay, because identically distributed. So I'll say this is equal to, if you will, the sum as I run from 1 to n of x of 1 raised to the 4, because they're identically distributed. So x of 1 raised to the 4, expected value of that, is the same thing as the expected value of x of 2 raised to the 4. Plus, I don't know how much I have in this sum here, but because of independence, here this is expected value of x of I squared times the expected value of x of j squared. Well, again, because it's identically distributed, that part can be simplified. And so can this. This is independent, if you will, or doesn't depend, it's a constant with respect to I. And so you have this guy done, added up n times. So it's n times the expected value of x of 1 to the 4. Okay, here, these guys are the same, okay? And whatever it is, it is. So if you will, this is some sum of the expected value of x of 1 squared squared. Now, how many of them are there in this term? Well, let's think. This is n times the expected value of x of 1 raised to 4. Okay. Well, how do I get, well, what is one of these guys that we're talking about? It's like saying x of 2 squared times x of 4 squared. How can I get that? Well, the x of 2 that was involved could come from the first or second, or the first and third, and of the groupings of the x of 1 added up through x of n. Any one of those four parts, two of them had x of 2 and two of them had x of 4 in my example. Okay? So when we're thinking how many ways are there to pick that many, well, that's exactly what we have. We're picking some. So we're saying, let's get the random variables involved. So let's think about it this way. We have n random variables, we need to pick two of them to get involved. So that's how many of these types we could have. One of which is x of 2 being squared times x of 4 being squared. That's one of them we choose to, because we have n random variables, we're picking two of them to get involved. Now, for each one of those n choose 2 pairings, if you will, of random variables to be involved in this form, we say how many of them are in that expected value of that multiplication that we had of x of 1 plus x of 2 all the way up to x of n times itself 4 times. Well, what you can think of is that you have those 4 x of 1 plus x of 2 all the way up to x of n's multiplied by each other. There's 4 groupings of them. And what we're thinking of is that we need to pick 4, out of the 4 of them that are there, we need to pick 2 of them to be, let's say, x of 2, and then the other 2 will automatically be the x of 4s. So that's what we have, times this expected value of x of 1 squared. Okay? So let me work with this just a little bit. This is equal to n times expected value of x of 1 raised to 4. Here, 4 choose 2 is 6. It's 6 n times n minus 1 over 2 times the expected value of x of 1 squared. That's what we are. So that's equal to n times the expected value of x of 1 raised to 4 plus, so this will be 3 times, well, n times n minus 1 times the expected value of x of 1 squared, all that to be squared. And what I want to say is this same thing, so I'll go slow for my sake, is that n times the expected value of x of 1 raised to 4 plus 3n squared times the expected value of x of 1 squared to be squared minus 3n times the expected value of x of 1 squared to be squared. Now this is a positive number, and we're subtracting it from the other guy. So this guy right here is smaller, is less than or equal to n times the expected value of x of 1 raised to the 4 plus 3n squared times the expected value of x of 1 squared to b squared. So what I just wrote is bigger than the line above it because the one line above it is taking away, has exactly this, but take away some positive numbers. The line above it is small. All right, well, note that 0 is less than or equal to the variance of x of 1 squared, which is equal to the expected value. So this is the random variable I'll talk about, x of 1 squared. If you were to take its variance according to the formula, it would be x of 1 squared, so x of 1 to the 4, minus the expected value of x of 1 squared to b squared. Well, I made a mistake here. This should be squared. So I forgot that part. So from this line that I've just written, what we can see is, since the expected value of x of 1 to the 4th minus the expected value of x of 1 to b squared, all to b squared, is greater than or equal to 0, that means that the expected value of x of 1 raised to the 4th has got to be bigger than or equal to the expected value of x of 1 squared to b squared. So this part right here is less than this part. So what that tells me is that the expected value of s of n raised to the 4th, which is what we're talking about, is less than or equal to
m times the expected value of x sub 1 raised to the 4th plus 3n squared, and let me replace this by x sub, the value, the expected value of the x sub 1 raised to the 4th. So we'll have the same thing involved. Excuse me. Okay. So if we divide everything by n to the 4th, so what we have is the expected value of s of n raised to the 4th over n to the 4th will be less than or equal to, well, divided by n to the 4th, so it will be the expected value of x sub 1 raised to the 4th over n to the 3rd plus 3 times the expected value of x sub 1 raised to the 4th, which we're assuming is finite, over n squared. Thus, the sum, as n runs from 1 to infinity, of the expected value of s of n to the 4th over n to the 4th, now these are all positive things, will be less than or equal to the expected value of x sub 1 to the 4th, well, the sum of this. Gosh, I didn't write that very well. The sum, as n runs from 1 to infinity, of x, the expected value of x sub 1 raised to the 4th over n to the 3rd, plus, I'll break this down into the other sum here, sum of this guy and sum of this guy, provided that each one of these things is finite. So this has a 3, expected value of x sub 1 raised to the 4th over n squared. And what I want to tell you is, the expected value of x sub 1 raised to the 4th is a constant. Okay? It's a finite value according to our assumption. And so this is a constant over n cubed. This is a constant over n squared. And we're summing these up. These are p series. And they will converge. Okay? They will converge provided the p, the power that n is being raised to, is bigger than 1. And they both are. Thus, well, this guy over here, this sum, is the same thing as the expected value of the sum. Okay, so this is finite. That's what I want to say. Give me a second. Is finite, because this part's finite and that part's finite. So, what that means is that the sum, as n runs from 1 to infinity, of s of n to the 4th over n to the 4th, that's n to the 4th, not 4 times n, is finite with probability 1. So the set that this guy is finite has probability 1, because otherwise, and that's what I'm going to write up here, if there was some region, some set for which this was not finite, when you take the expected value, you wouldn't get a finite number. Okay? So that's what I'm going to write. Excuse me. So because if not, then there would exist a set whose probability is non-zero, such that the sum, as n runs from 1 to infinity, of
of s of n raised to the fourth over n to the fourth is infinite. And thus, the expected value of this set, of this function, would be infinite. But it's not infinite. Okay. So just to reiterate, so this sum is in run from 1 to infinity of s of n raised to the fourth over n to the fourth. Okay, is finite with probability 1. Okay, that's what we're writing. Okay, so what does that mean? It's finite with probability 1. So what that means is with probability 1, okay, so that's almost surely. For this thing to be finite, so this is a sum, by the divergence test, probability 1, the limit as n goes to infinity of s of n to the fourth over n to the fourth has to go to 0 by the divergence test. Because of finite convergence. So that implies with probability 1 that the limit as n goes to infinity of s of n over n will be equal to 0. And that's what we wanted to show because that's mu, okay, is 0. So this proves it for the case where mu is equal to 0. So that's what we have. So I'll just say it more clearly. Thus, the limit as n goes to infinity of x of 1 plus x of 2 plus all of x of n over n, that part is equal to 0. That's our mu with probability 1. Okay, case 2. For case 2, suppose mu is different than 0. So that was the expected value, the mean for each random variable. Suppose it's not 0. Not 0. Then consider the sequence of random variables I'm going to call them x of I star, defined by so there are x sub I, the random variables in our original sequence, minus mu. So x of I star, so it's clear, is equal to x sub I minus mu. Consider that. So the x of i's are our random variable in our original sequence. Now I'm looking at a different sequence. Well, the first thing to notice is that the x of I stars will be, so x of 1 star, x of 2 star, forever, will be a sequence
of independent and identically distributed random variables because of their definition and the fact that the x of i's are a sequence of independent, identically distributed random variables. Okay? Also, the expected value of x of I star will be equal to the expected value of x of I minus mu, where mu is the expected value of x of I. So that's the expected value of x of I minus, and the expected value of mu is just mu, but that's mu minus mu, which equals to 0. So, by case 1, the limit, so by case 1, what do I mean by that? I'm going to apply case 1 to the sequence of random variables x of I stars, okay? Because they are independent, identically distributed, whose mean is 0. Okay? We have, with probability 1, the limit as n goes to infinity of x of 1 star plus x of 2 star plus all the way up to x of n star over n, that's equal to 0. We're almost done. So with probability 1, the limit as n goes to infinity, what's x of 1 star? Well, then x of 1 minus mu plus, then we have x of 2 star. That's x of 2 minus mu plus, and so forth, all the way up to x of n minus mu over n will equal to 0. So with probability 1, the limit as n goes to infinity of x of 1 plus x of 2, reorganizing these, all the way up to x of n over n factorial minus what? We got mu, mu's, we got n of them over n, so that's minus mu will equal to 0. So with probability 1, the limit as n goes to infinity of x of 1 plus x of 2 plus x of n over n equals to mu. And that's what it is that we wanted to prove. We proved it in all possible cases. And that concludes the proof with that extra condition of the expected value of the x of I is raised to the 4th power being finite. That concludes our proof of the strong law of large numbers. Thank you very much for your time and patience.